everybody. So today we are going to be talking about the aquatic section of the Envirothon test, and I'm going to be moving through a number of topics fairly quickly, and there are going to be some things that I'm going to point out to ask you to review on your own. So just be on the lookout for those. You will be needing to do some research on your own time, and then if you have any questions for me during the question and answer session, I am happy to answer those. So there are four main components of this training that we're talking about when we're referencing aquatics. So there are the abiotic factors, the non-living things, the biotic factors, all the living things, a bunch of different aquatic environments that all have different biotic and abiotic factors, and then water protection and conservation, which is kind of a diverse, large topic. So let's dive right in. The base of all of this is the water cycle. So we all learned about the water cycle in school, but it's a lot more advanced than what they generally cover in our science classes. So the basics of it are, starting in the ocean, water evaporates because of higher temperatures, ends up in the atmosphere where it condenses into clouds because of cooler temperatures. Once those build up enough, it comes down again as precipitation, either snow, rain, hail, sleet, whatever precipitation we're feeling. Lands in a bunch of different places, sometimes directly onto the ground, sometimes in lakes, rivers, or oceans, sometimes on top of mountains. It's really cool. So it lands on the ground and it either infiltrates into our groundwater or it goes across the surface as runoff, collecting things along the way, or sometimes it just ends up straight back into the water. It can also be drank by an animal, absorbed by a plant. Like, there's so many different things that can happen with the water, but those are the basics. And as you can tell, it's all driven by temperature and on a larger scale by climate. And so temperature and climate have a pretty large impact on our water cycle and on our water quality. So climate change, which is, the changing of our climate, is a huge topic right now, definitely impacts our weather and our water cycle. So higher temperatures mean there is more evaporation from the land and sea into the atmosphere. So more water is leaving the land and leaving more things behind. And then once the air gets warmer, it can hold more water vapor, which leads to more intense weather. So water temperature, the temperature of the air and the water are what controls our entire global water cycle. So the movement of our currents and our tides and things like that. And so as the global temperature increases, those cycles are also being impacted. And then intense rainstorms, intense weather events increase the risk of flooding, more damage to homes, businesses, things like that. And then a lot of that water, because there's so much more of it at such intense rainfall, it runs off into our rivers and streams and doesn't actually get the chance to infiltrate and replenish our groundwater. The increased temperatures that increase our evaporation also increase our risk of drought, because that means our soil is losing more water more quickly. The soil is forming this really hard crust on top, and so it's harder for water to infiltrate when it does come down, so more of it's running off and just creating these really dry, cracked, gross surfaces. The water cycle also has impacts on our soil. The water cycle is not just water, as you guys know. The water is also impacting just like everything on the planet. So like I said, higher rates of evaporation are leaving behind more nutrients and minerals, and this can sometimes cause something called salinization. So salt is just another mineral that can be left behind, and with more water evaporating, more salt getting left behind, that creates really salty soil that decreases crop production. It has like a really major impact on our agriculture. It also leaves behind more nutrients in general, so things like nitrates and phosphates that then can get into our groundwater supply, or when we do have these large rain events, can collect and run off and end up in our watershed, in the water. So it does have like a large impact on our agriculture, the overall health of the watershed, and of the water that we use every day. So I'm talking a lot about watersheds in this water cycle, so let's talk a little bit about what that means and what those are. So watershed is an area of land that drains water, sediment, and dissolved materials into a common receiving body or outlet. So watersheds can be for lakes, for streams, for rivers, for bays, for oceans. Like, they can be different sizes and on different scales. So in Virginia, we have 14 major watersheds, and they're all color-coded here. These are something I definitely recommend you guys take a look at and study, because I grew up in tidal Virginia over in the northern neck, and so I just thought that all water in Virginia drained to the Chesapeake Bay, not the ocean, growing up. But that's not true. Of the 14, there are actually only 5 watersheds that drain into the Chesapeake Bay, which are the James, the Potomac, the Rappahannock, the York, and then these really small coastal watersheds that just drain directly into the bay. I always remember the order of rivers and also the ones that drain into the Chesapeake Bay by the saying, please remember your jacket, Potomac, Rappahannock, York, James. That's also the order that they are on our coast. So please remember your jacket. Those are the 4 rivers, and then there's also the ones that just drain directly into the bay. So 5 watersheds that go directly into the Chesapeake Bay here in Virginia. That's cool. How do you know what a watershed is? So watersheds are separated by boundaries, which are usually some sort of mountain or elevation change, because water can't flow uphill. There are also the watershed boundaries that are just natural because like it's the end of a river, it's not going to flow anymore past those headwaters, and so another river just takes over and flows somewhere else. So our watersheds are marked by something called delineation. So it's the whole practice of identifying where your watershed is. So the first step is getting familiar with topographic maps. And if you aren't familiar with topographic maps, I do think that's something you should spend a little bit of time learning and familiarizing yourself with. So topographic maps have these topo lines that show us different elevations. So on most topo maps, there are elevations written into the lines, so you know kind of which direction they are. So the way we start is by identifying what watershed we want to delineate. So on our left map here, our step 1, you can see there's a little blob with lines in it and a circle at the bottom. So the circle is on the area that we're looking at, and then the lines are a wetland that's near that. So we're looking at this wetland and what is the watershed that feeds into the wetland. And so what we're going to do first is, after we identify our starting point, we are going to go out from our starting point and find our peaks. So you see the topographic lines, they become concentric circles and they build up to one peak right there at the top. And so you go around and you mark all those peaks, because like I said, water doesn't flow uphill. It's flowing downhill from these points into a basin. So water starting at the top there is going to go one way or the other, left or right, east or west, and it's going to flow into our basin here. So we mark with X's all of our peaks in the area. And then you just go through and you connect those peaks with a line, and you can see that is where all of the water that is draining into our watershed. So this is a watershed for one specific point. It's the Nelson River, I think. This is actually from New Hampshire, so this is not a local one. But this is one water body, and there can actually be tributaries of that water body. So watershed can be broken down in a lot of different ways. So like I said, there's the Chesapeake Bay watershed, which is a really big one. There are 5 major rivers. It spans 6 different states, plus Washington, D.C., so it's a huge one. And then within the Chesapeake Bay watershed, there are smaller ones, like the James River, the Rappahannock River, things like that. And then off those rivers, there are smaller streams and creeks. So there are watersheds within watersheds. And within those watersheds, there are different streams. So you have your major river, and then little branching streams off of it. And so something to think about with that is stream order. So within our watershed, we have different streams flowing into the other streams, and we need to pay attention to the stream order, which is a method of assigning a numeric order to links in a stream network. So streams flowing into each other, tributaries flowing into each other to a main water body. It's a really important thing to do because it helps us identify and classify types of streams based on the number of their tributaries. And the number and type of stream is important because the characteristics of those streams can be inferred just by knowing what order they are. So it starts at 1, 1 is the smallest, and it goes up to whatever number you end up with depending on how many tributaries and streams you're looking at. But these characteristics are important because like first order streams, which are the smallest ones up at the headwaters, those are primarily fed by overland flow of water, so things like runoff, precipitation at the top of a mountain trickling down into the stream. They don't have any upstream concentrated flow. So they're really, really susceptible to non-point source pollution problems, which is something we're going to talk about kind of near the end of this presentation. But non-point source pollution is pollution that comes from runoff, that comes from water traveling over surfaces, be it just the land, parking lots, things like that. So because these are small streams and most of their water is coming from overland flow, they're really, really susceptible to non-point source pollution, and can be something you need to like pay attention to when you're looking at the health of our river, health of our watersheds, and they can derive more benefit from wide riparian buffers, which is something else we're going to be talking about later. So there are two different methods of determining stream order. There's the Strahler method, I actually don't know how to say it, versus the Shreve method. So the Strahler method, you can see here we've only got 3 numbers on the stream, on the photo. You start at the top with 1. When 2 ones connect, they make a 2, but when a 2 and a 1 connect, they just make a 2. So the only time you increase the number for the Strahler method is when they're the same number coming together. 1 and 1 makes a 2. 2 and 2 makes a 3. But if it's a 1 and a 2, that smaller stream just adopts the order of the larger stream. So 1, 1, 2, 2, 1 is 2. 2, 2 is 3. It's not additive, it's building on top of each other. So 2 and 2 isn't going to be 4, it's going to be 3. It's just the next number in the order. The other one is the Shreve method, which is building on top of each other. So you still start with 1, because of course that makes sense. And so you have 2 streams of the order 1 come together, that makes a 2, makes sense. But if you have a 2 and a 1 come together, they make a 3. You have a 3 and a 1 come together, that makes a 4. The 3 and a 4 come together, it makes a 7. So it's building on top of each other, and it's a really additive method of stream order. So when you're talking about and thinking about stream order, you just need to decide or know which method you're being expected to use. And that's going to really impact what you're thinking about, because the Strahler 3 is the same as a Shreve 7, which is such a huge leap in numbers. So just make sure that's something you're aware of as you're calculating stream order. And if you get questions about this, they are going to say use X or Y methods. So make sure that you are familiarizing yourself with both. So we're talking about watersheds, and the whole point of this is how do we keep them healthy? There are a couple of different components to watershed health that you all need to be aware of. First of all is water quality, and that can be measured in a couple of different ways. You can use chemical water quality tests, or you can use biological metrics to determine your water quality. Second is soil health. So soil health is so important to the watershed, because when people think about watershed, they get tripped up because it has the word water, but it's actually talking about water, land, people, everything within that watershed. So soil health is really important. You want to know how quickly it's weathering and eroding away. Is there a stream bank issue? Are there pollutants being carried? As well as the salinization of that soil and the buildup in minerals, depending on how much evaporation and extreme weather events we're experiencing. You also want to think about the biodiversity of the flora and the fauna. High biodiversity is usually a good thing. You want more species, that means there are more resources to go around to everyone. But in that, you also want to pay attention to the presence or the absence of invasive species. If you have a bunch of different species, but like half of them are invasive, are we really benefiting our watershed? Because once you have more invasive species, your biodiversity is eventually going to go down, because they're just completely going to take over. And something to note is the difference between invasive and non-native species. So both of them are introduced to an area. They're not from there. They're all non-native. Ones that don't do any harm, that just kind of live and fill their own niche and do their own things, they stay non-native species. But as soon as they start harming the environment, outcompeting native species, or like actively harming other species, that's when they become invasive. So all invasive species are non-native, but not all non-native species are invasive. And then you also want to look at the health of sub-watersheds. So you can look at, for example, the Rappahannock River, which is where I work. You look at the whole river, but then you also look at some of those creeks that feed into it, like Mount Holly and Toteski and all these small ones that run into the larger river, because your tributaries are directly impacting the health of the whole watershed. So say the whole watershed has a grade of C-, but you have a couple of tributaries that are like a D-. When you're looking at the watershed grade, you really want to make sure you're focusing on those tributaries, because they could be the ones bringing down the whole score. So, chemical water quality testing. You can do this a bunch of different ways. So you can buy little chemical water quality kits. You can buy actually more advanced equipment, but it all measures the same thing. So when we're testing for chemical water quality, there are 6 really common tests that we do. So there's the pH, which is just how acidic or basic the water is. 7 is neutral. Between 6 and 8 is where most species want to live. If it gets too acidic, they can't live in it because it literally starts dissolving them, and if it's too basic, they're not going to thrive in that either. So 6 to 8 is usually our desired pH. Dissolved oxygen, which is measured in parts per million, generally you want it over a 4. The size of your water body is really going to impact that, as well as how much your water is flowing. So water that's flowing more has actually a higher dissolved oxygen because it's able to kind of do some more turnover, and oxygen can infiltrate it. Colder water also holds more dissolved oxygen, so it's just something to keep in mind as you're going through these tests. You can do that either with a probe, all of these really, either with a probe that you stick into the water and it comes out to a reader, or you can get little test kits with either tablets or drops that you put into the water and it reads out what your water quality is, or like that specific parameter is, and that takes a little bit more interpretation because it's usually like by color, and so you have to look at the little cards and see what it is. So that's just something you get comfortable and familiar with. You also want to test for nitrates and phosphates. So nitrogen and phosphorus, these are things that are present in fertilizer. And I always think of nitrogen and phosphorus as dessert. A little bit of it is really good. You want some nitrogen and phosphorus in your system. It's what helps plants grow, so subaquatic vegetation as well as riparian, or like streamside areas, riverside areas, they need nitrogen and phosphorus to thrive. However, if you have too much of it, it's bad for you. So dessert after dinner is awesome. Dessert all day long, constantly, is not great. So that's the same way you want to think about nitrogen and phosphorus. And you generally want those under 2 parts per million when you're taking your measurements. You also want to check for temperature. Like I said, cooler water holds more oxygen, but warmer water are what some species need to survive. Like manatees can't survive under 70-degree water. That's why we don't have manatees in Virginia. And then turbidity, which is a measurement of the suspended solids in the water. And that's something where you use a Secchi disc, which is a black and white disc, and you lower it into the water and see how far down you can still read it. When we're talking about chemical water quality, we also want to make sure we're paying attention to TMDLs, which is the total maximum daily load. That's a regulatory term in the U.S. Clean Water Act, which describes a plan for restoring impaired water, identifying the maximum amount of a pollutant that a body of water can receive while still meeting water quality standards. So most water bodies in the U.S. have a TMDL associated with them, but each one is specific to the water body, and it's determined by state agencies. So it really just depends on what the goals are, how impaired it currently is, all of the different factors influencing how much water there is, how fast it's flowing, things like that. So TMDLs are something to just pay attention to. If you're ever going out to do any sort of research, you want to pay attention to those for your water body. There's also biological water quality testing, and that relies a lot on indicator species, which is an organism whose characteristics are used to point out the presence or absence of environmental conditions that can't be feasibly measured from other taxa or the environment as a whole. So indicator species are special because they're either very tolerant or not tolerant at all. They have a very specific set of parameters that they can exist within. And so if you're seeing those species, then that indicates the health of the water. 3 of the common ones are benthic macroinvertebrates, amphibians, and fish. So benthic macroinvertebrates and fish are kind of measured the same way. You look at them, some of them are tolerant, some aren't. If you're seeing a ton of the pollution-tolerant species and none of the intolerant ones, then that gives you an idea that your water probably isn't super healthy without having to do any of the chemical tests. Amphibians are kind of unique because amphibians breathe through their skin, and they have really, really sensitive skin. So if you see amphibians in the water, generally your water quality is pretty decent. Because they just can't exist in poor water quality because it just seeps into their skin, and that's not great for them. You want to know for benthic macroinvertebrates and fish and things like that, no one expects you to memorize all of the benthic macroinvertebrates there are in the world. So that's a time to really get familiar with a dichotomous key. You haven't used one before, it's just a system of identifying flora, fauna, kind of anything where you're answered a series of yes-no questions, or you're asked a series of yes-no questions, and your answers determine kind of where you go in the next step, kind of like a choose your own adventure, but at the end you get to identify a species. And this is something you should probably take a look at for your test, because like it is like such a good indicator of water quality. And within these, looking at biological water quality, food webs are really important. So you can look at all the benthic macroinvertebrates and fish that you want. but you really need to look at it as a whole picture. No organism exists in its own bubble apart from everything else. So you might be seeing a ton of diversity of benthic macroinvertebrates, but what if there are no predators around? So that means they have a food source, but they don't have anything eating them. And that also isn't good for our water quality because we want that diversity. We want the food web to keep moving because these arrows are going everywhere. Everything is impacting everyone. So it starts with our producers, and then there's our low-level consumers. So our zooplankton eat our phytoplankton, our planktivorous fish eat our zooplankton, our piscivorous fish eat our smaller fish, and ducks and wading birds and things like that. So you want to be paying attention to these food webs and making sure you're not missing a huge link. So say you have a ton of phytoplankton, a ton of zooplankton, but you don't have any planktivorous fish. Where are the fish? Why aren't they living there if this is a habitat that they're used to? So this just can help you piece together a full puzzle of an environment and of an ecosystem without looking at just one specific piece. You really want to be critically thinking about this and what it all means together. This is also important for the concept of biomagnification. So when we have pollutants in our water, you see that it moves at these trophic levels from our producers, our lower level, higher level, top predators. And if there is pollution in the water that's getting into these producers or these really low level consumers, and then they're eaten by bigger things, the pollutants are going to build up in their body, and that's a really big issue. So just something to pay attention to. Mercury is a really big one, impacted by biomagnification. Also in our food webs, talking about our environments, we need to think about carrying capacity. So the carrying capacity refers to the competing needs within a system, where a system can only hold so many organisms. There's only so many resources, and K, which is our carrying capacity, is that equilibrium. So that is where all the resources are being used by everyone, and there's no extra resources, there aren't too few resources, everyone's just kind of existing at this level. And a lot of competing needs within a system can affect that carrying capacity. It can shift over time, there can be different resources available or depleted, and you can see that it's really a logistic S-shaped curve. So there's slow growth at the beginning, the growth rate decreases as carrying capacity is approached, and then fast growth, like the population is increasing over time, there are plenty of resources, but then you hit a certain level where it just levels off, the birth rate decreases, or the predation rate increases, or however it happens, but an ecosystem can only host so many organisms of all trophic levels. So this isn't just like a certain number of deer specifically, it's everything competing for, water or food or whatever the resource is. It's a huge system all interacting together. So we are going to move into a little bit more specifics. We're going to start talking about wetlands, which are one of my favorite things to talk about, so I'm really excited today. So we've talked about our watersheds on the whole, and wetlands are a really important part of watersheds. So there are 4 major types of wetlands: marshes, bogs, swamps, and fens. And within each of these 4 major types of wetlands, there are subtypes. So like marshes, there are non-tidal and tidal marshes, and even if within non-tidal marshes, there are specific types of non-tidal marshes. And each of these types of wetlands has a specific set of characteristics and a specific functionality and value to its community. And so I'm going to go over the 4 major types, but it's your responsibility to go through and look at the subtypes of wetlands. First of all, marshes, which are my favorite type of wetland. So marshes are really cool. They are wetlands that are frequently or continually inundated with water. So non-tidal wetlands, the water's just sitting there. Tidal wetlands, they're on a tidal cycle. But they are inundated with water at least 50% of the time. They're really characterized by emergent soft stem vegetation, adapted to saturated soil conditions. So they're hydrophilic plants. They're used to being in wet soil. Sometimes wet soil can cause plants to need specific adaptations because oxygen doesn't come into our soil as easily as it goes out of our soil when it's wet. So they just have a specific set of conditions. In salty tidal wetlands, for example, you'll see a lot of Spartina alterniflora and Spartina patens. Those are pretty much all you're going to see unless they're invasive species because they are what are specifically adapted to that environment. These are cool because most of the water is received from surface water, so either flooding, tides, flowing over the surface, but it's also partially fed by groundwater. So they can get water from a couple different sources. And they're so productive. There's tons of nutrients. There's such productive environments. They're great to have around, and they have a ton of functions to humans and to animals. So they recharge groundwater supplies, and they moderate stream flow, which is super important during droughts, however you want to say it. They also mitigate flooding. So when a river starts to flood, they act as a buffer to houses, to the rest of the environment, and kind of slow that flooding down. They also act as natural filters. So as water runs off across the land, it hits the marsh and it slows down because of all of those soft stem vegetation, and it's absorbed into the soil, which is naturally a filter. The way it's made up of detritus, which is just broken down organic material, it filters out all the nutrients and things that you don't want to get into your open water. And then they also act as nurseries for some organisms, like blue crabs use them as nurseries, some fish species, things like that. So they're also a great source of food for that reason, though, because there are baby animals, there are shellfish, things like that that live in them. Great source of food and habitat for upland animals. Second, swamp. So this is a wetland, so still wet at least 50% of the time, but it's going to be dominated by woody plants, either shrubs or big trees, but it's got that woody stem. So the soils are totally saturated during the growing season. These are also hydrophilic plants. And then they have standing water during certain times of the year. So they don't need to be obviously very wet all of the time, but the soil is pretty much always saturated to some degree. And they have these really great organic soils that are like thick, black, nutrient rich, really beautiful soil. That's like just beautiful to grow things. And it smells really funky. And like I said, a lot of hydrophilic plants. They are also great for flood protection. You're going to start seeing a pattern here because wetlands are super important for a lot of the same things. They also help with nutrient removal and act as that filter. They are very highly productive environments that host a high diversity of species. There are so many nutrients available that the plants can grow. You can get a lot of species diversity, which then goes up through the trophic levels and allows more species to thrive. And they can, because there are hardwood swamps, they can be a really important source of timber because, like I said, that soil is really nutrient dense, so that wood is really nice, but they need to be sustainably harvested. They can't just be clear cut. Next up, we have bogs. They have spongy peat deposits. If you walk in a bog, it's going to be like a very bouncy, it's not soil, it's peat, bouncy floor. But they really acidic waters. That's kind of a trade-off. Bogs are interesting because they're all about sphagnum moss, and I really encourage you guys to look up sphagnum moss. It is a really cool organism. It actually has healing properties, and a lot of native populations use it in a healing way. You can filter water through it. It's just like an everything plant, and I love it. So sphagnum moss is the driving force behind bogs. So bogs can be formed in two different ways. Either sphagnum moss can grow over a wet environment, so a lake can get covered by sphagnum moss. It's called terrestriation, where it fills in that lake, or they can come to a dry environment. Sphagnum moss can grow over the dry environment and trap water. So it's either making a wet environment drier or a dry environment wetter using moss. They're entirely fed by precipitation. They don't have groundwater or like a stream or anything flowing into it. It's all precipitation. They're super low in nutrients and high in acid, like I said before, and so they have really specific plant and animal communities with special adaptations. So it's this really unique and demanding environment. But they're great because they prevent downstream flooding. Again, wetlands are great for preventing flooding. They also absorb precipitation, so when we get those huge rainfall events, because they are entirely fed by precipitation, they absorb all of that, and they just suck it right up. They also support unique plant communities, specifically carnivorous plants. Bogs often have a ton of carnivorous plants, and they're just so cool for this unique, it's not diversity because it's only a few types of plants, but they're really cool plants. And then they also protect animals from human encroachment. Humans don't want to use bogs. They're super acidic, they don't create good soil, and they're kind of gross for humans, and so we don't want to use them. Humans, though, because bogs and swamps and marshes and stuff, if you look at media, they've all been kind of demonized, especially bogs and swamps. And so a lot of humans ended up draining bogs and swamps and marshes and things like that, either to build because they're right on the water, or because you think of like the movies and stuff where there's a bog monster, a swamp monster. Humans just have this really negative view of wetlands. And so that's something just to keep in mind when we're talking about conservation, is the perception as well as these functions and values. And then finally, there are fens, which are also peat forming, but they receive nutrients from sources other than precipitation. And that is a typo. So they have drainage from the surrounding soil as well as groundwater. So they're similar to bogs, but they have much higher nutrient levels and they're less acidic. And they have a more like common group of plants, so grasses, sedges, rushes, and wildflowers. And they also have these really cool ridges on hollows. So they'll have these areas that are kind of these parallel lines where it's a ridge of high productivity with a ton of flowers and plants on it, and then these hollows, these valleys in between the ridges that aren't as productive. And they, again, prevent or reduce the risk of flood, improve water quality, and they create a unique habitat for plant and animal communities. So if you're seeing the pattern here, all wetlands prevent flooding, improve water quality, create a unique habitat, and filter nutrients. On either side of these wetlands, on all of our waterways, we want to consider riparian zones. So it's the area where terrestrial and aquatic ecosystems converge. And it's an early successional habitat. You can see in the pictures, there's the aquatic zone, the riparian zone, and the uplands. And so the riparian zone can handle some flooding, but not frequent flooding the way that wetlands can, because it's got a mix usually of like wetland plants as well as woody vegetation that can't handle as much of that. So it occupies the space above ground, but there are also below ground processes like the root processes that are equally important for protecting these aquatic systems by filtering out nutrients, shoreline stabilization, things like that. And they have a super high diversity because they're part upland and part wetland, with like partial flooding. So it hosts a whole lot of species of plants. Riparian zones are super beneficial. They provide essential wildlife habitat. They regulate aquatic temperature through shading. So on those hot summer days when trees are full of leaves, they keep our streams and other smaller water bodies from reaching unsafe temperatures because, like I said before, cooler waters, more dissolved oxygen, more organisms can live in them. Leaves and small twigs also fall from these plants and act as a food source. Fallen trees can create really cool structurally diverse microhabitats within stream systems. And like I said, they prevent erosion, they slow runoff, and they act as natural filters. So when we're talking about like mitigation techniques, especially for agricultural places, so you have a field that has cows or crop production, you've got a stream running down the middle. One of the most common recommendations to protect that stream is a riparian buffer because it keeps animals and stuff out of the stream, especially if you use fencing with it, and it absorbs all those nutrients and really just keeps that stream like safe. It's kind of like a nice cozy sweater around your stream. Now we're going to move on to aquifers, which are kind of a different sort of aquatic habitat, except nothing lives there. So aquifers are interesting. They're a body of permeable rock which can contain or transmit groundwater. So a lot of people think that aquifers are just like almost an underground lake, like it's a blob of water under the ground, but really it's a porous rock that holds on to water. And there are a couple different aquifers that we should be aware of. There's confined versus unconfined. So confined aquifers are completely filled with water and surrounded on all sides by confining beds, which are just an impermeable rock or sediment that's holding that water there. And the only opening to the outside world is at the top at its recharge zone. And so water is under pressure constantly. And so they're also called artesian aquifers, which you might recognize from artesian wells. So artesian wells are drilled down into these confined aquifers, and the pressure from the aquifer pushes the water up. So you don't need an artificial pump system. There's natural pressure. And there are also unconfined aquifers, which are not bound by confining beds. So there's usually a bed on the bottom that's impermeable, but then the top is exposed to a lake, a stream, other groundwater. It's not like stuck, and so it's not pressurized. And so the water table rises and falls as the amount of water fluctuates, like I said, because it's not pressurized. But they also get wells called water table wells. And those have their own unique set of like challenges and benefits. So both type of aquifers must have recharge areas that are protected from land use activities that might contaminate that aquifer, because aquifers are groundwater, and groundwater is also subject to pollution and land use problems. So here's just a graphic again, kind of explaining the confined versus unconfined aquifers, and kind of what that looks like, so you can see it all together. So humans have a lot of impact on aquifers. So like I said, since it's groundwater, it can become contaminated through human activities. So we need to make sure we're protecting that. One of the most modern examples that has been in the news a lot is fracking. So that's a way of harvesting natural gas where you literally go down and like fragment the earth to release the gas, but they use a lot of chemicals in that process, which are then directly put into the groundwater. And groundwater moves really slowly. It doesn't move like our surface water does, so contaminants can remain for hundreds of years, which is another typo, sorry guys. And then there's also the creation of cones of depression. So if you're putting a ton of confined and unconfined wells, so like water table wells and artesian wells all in the same place, and everyone's drawing a lot of water, it can create these cones of depression, where there's a decline in water level in the aquifer and subsequently a decline in pressure because of how many wells there are, and it can make your well less effective. And then large groundwater withdrawals are also a pretty significant concern. All right, let's talk water pollution because we just talked about human impacts on our aquifers. So water pollution can be point source or non-point source. Point source pollution, as it sounds, come from a single identifiable source, like in this graphic, like the wastewater treatment plants with the outflow point, a factory, things like that. And then there's also non-point source pollution, which I think is more common, and we talk about a lot more because it's so much harder to regulate and control. So non-point source pollution comes from runoff. So when rainfall or snowmelt moving over or through the ground picks up and carries pollutants into lakes, rivers, wetlands, watersheds, coastal waters, groundwater, any water. So water is super greedy. As it flows over the ground, it just picks up everything and carries it into the water. So tons of non-point source pollution. That's what we were talking about with our streams earlier. Our first order streams are super subject to non-point source pollution. Another big issue that we were just talking about is water conservation. So water conservation is all the policy, strategies, and activities to sustainably manage the natural resource of fresh water, to protect the hydrosphere, and to meet the current and future human demand. So like when I was talking about those huge taking water out of our aquifers, so like draining our aquifers of their water, that's a big giant problem, and where water conservation comes in. So there are a lot of competing water uses that all need to be managed, and there are a lot of key strategies for that. So things just like reducing our use of water. So turn the faucet off while you're brushing your teeth and washing your hands and things like that. Also making sure you're like replacing your pipes so that you're not losing water, contaminating water, and just kind of keeping an eye on how we're using our water. Also protecting our water quality. Water that is contaminated cannot be used. And also improving our water management practices to reduce use or enhance the beneficial use of water. So things like rainwater harvesting, updating our infrastructure for less water loss, innovations in irrigation, stuff like that. And this is managed all on a federal and state level. So not just our water conservation, also all of our water use and how that impacts our environment. So at the federal level, we have the EPA, the Environmental Protection Agency, the USGS, NOAA Fisheries, U.S. Fish and Wildlife, so many more, because like I said, water doesn't exist in a vacuum. Everything's connected, so everyone works together on this. Here in Virginia, we have the Soil and Water Conservation Districts, as well as DCR, who are the people in charge of state parks, who are very cool. And then at the local level, each locality is structured very differently, but every single locality, be it county, town, village, hamlet, whatever, has some sort of water, environmental, compliance, or natural resource person on staff to help manage our water use and water protection. There are a lot of federal laws and regulations. This is something I'm going to ask you guys to familiarize yourself with outside of this presentation. So there's the Safe Drinking Water Act, which just like regulates our drinking water. And there are federal standards, and states are allowed to have stricter standards. There's the National Environmental Policy Act, which requires federal agencies to think about the environment when they're making decisions, permitting, land use, things like that. And then there's the Endangered Species Act, which recognizes the natural heritage of the United States was of aesthetic, ecological, educational, recreational, and scientific value to our nation and its people, and so the government has the responsibility to protect all of these species, which it's important to know the distinction between these: threatened, endangered, and then critical habitat, which is, again, something I'm going to ask you guys to research on your own. Also, regulation of species is aquatic nuisance species. So these are non-indigenous species, also called invasive species, that threaten the diversity or abundance of native species. or any negative impact they have on the ecology or use of the water. So they're commonly introduced as a direct result of human activity, either in ballast water, through contaminated fishing gear. Sometimes you intentionally stock areas for other species management, or bait just gets released. And then state and federal agencies work together to protect aquatic habitats and prevent those who use our waterways from inadvertently transporting ANS. And so this is, again, state, local, federal, everyone's collaborating to keep our waterways happy and healthy. In Virginia, we have an ANS task force and a Virginia invasive species management plan with 7 key steps. Our 6 Virginia species that have been qualified as ANS are zebra mussels, snakehead fish, quagga mussels, New Zealand mud snails, rusty crayfish, and black carp. These are not all of the invasive species that are found in Virginia. These are just the ones identified by this ANS task force as the highest priority.